Hello everyone, I'm Durga Pavan Kumar. I'm here to explain you convolution in 1D and 2D. What is convolution? Convolution is an integral that expresses the amount of overlap of one function when it is shifted over another function. Where we use convolution? Convolution can be used to find the output of an LTI system when input is applied. Nothing but y of t is equal to x of t convolution with h of t, where x of t is input signal and h of t is impulse response of LTI system. One of the property of convolution is convolution of two signals in the time domain is equivalent to multiplication of their representation in frequency domain. Now let us see mathematical representation of convolution. Y of t is equal to x1 of t convolution with x2 of t, which is equal to integral minus infinity to infinity x1 of p into x2 of t minus p dp. Here x1 of t and x2 of t are two functions and y of t is the output signal function. Star represents the convolution operation. Now let us understand different steps involved in calculation of convolution of two signals. Consider two signals x1 of t and x2 of t. In case of finding output of an LTI or LSA system, one signal will be impulse response of the system and other will be input signal. In the second step, change the independent variables in both the signals just for sake of clarity. We will replace t with p in both the signals. Apply time reversal on any one of the signal. Let's say I'll apply on x2 of p, it will become x2 of minus p. In the fourth step, we will apply time shifting on x2 of minus p, it will become x2 of t minus p. In the final step, we will multiply both the signals and integrate over the limits from minus infinity to infinity. Let us take a look at the convolution of rectangular and triangular signals practically. As we can see, time reversal is applied on triangular signal and it is shifted and slided over the rectangular signal over minus infinity to infinity, and the both signals were multiplied over the limits. We can observe the output signal simultaneously, which is in the pink color. In addition to 1D convolution we discussed before, the process of convolution can be carried out on multidimensional signals too. Let us take a look at 2D convolution now. Convolution involving one-dimensional signal is referred to as 1D convolution or just convolution. If the convolution is performed between two signals spanning along two mutually perpendicular dimensions, that is nothing but if two signals are two dimension in nature, then it will be referred as 2D convolution. This concept can be extended to involve multi-dimensional signals, due to which we can have multi-dimensional convolution. In the digital domain, convolution is performed by multiplying and accumulating the instantaneous values of the overlapping samples corresponding to two signals. To be more precise, in 2D convolution, operation is done by multiplying a pixels and its neighboring pixel color value by a matrix. Here matrix is nothing but a kernel. A kernel is usually a small matrix of numbers that is used in image convolution. Different size kernels contains different patterns of numbers, produce different results under convolution. Usually kernels will be in 3 into 3 matrix size. We can see an example below here, a matrix 3 into 3, which like in the representation H. Let's understand 2D convolution better with an example. Here we have 4 into 4 matrix or image and a kernel of size 3 into 3. Proceeding forward, let's understand the steps involved in 2D convolution. First step is kernel inversion, nothing but transpose of a matrix. We will transpose the kernel here. In the next step, we need to do zero padding. When there are no image pixels to overlap the kernel pixel, the operation of adding 0 is known as zero padding. We will slide the kernel over the image and perform MAC operations at each instance. MAC stands for multiply and accumulate operation. We will overlap the inverted kernel over the image and do advancing pixel by pixel. Here, for each case, we will compute the product of mutually overlapping pixels and calculate their sum. The result will be value of the output pixel at that particular location. Now we will start sliding the kernel column wise first and then advance along the rows. During this process, the first overlap between kernel and the image pixels are shaded with yellow color. You can see clearly. And we will do MSC operation on coincident pixels. So the first pixel value of the output image will be 0. Next, let us advance the kernel along the same row by a single pixel. We will multiply and add the shaded matrix. The resultant output pixel will be 3. The next step would be advance vertically down by a single pixel before restarting to move horizontally. Following this, we will slide the kernel in horizontal direction till there are no more values which overlap between the kernel and the image matrix. The process of moving one step down followed by horizontal scanning has to be continued until the last row of the image matrix. A random example concerned with the pixel output at the location 3.3 shown below. The output is 7. By following the before mentioned step till the last pixel value in the input image, the resultant output matrix of the convolution is obtained here. Here we can see the resultant image. In this example, we can see how the overlap of kernel happening and multiplication and addition taking place to get the output. Here, like a visualization is very clear. In this presentation, we discussed about 1D and 2D convolution and the steps involved and its mathematical calculations. Thank you.